Section 13.3 is concerned with what happens when we shift a system away from equilibrium, and this is summarized by what is known as Le Chatelier's principle. So Le Chatelier's principle states that if we make a change to a system that's at chemical equilibrium, the system will spontaneously return to the equilibrium position. And this idea is named after Henry Louis Le Chatelier, who was a French scientist, and he kind of figured this out. So let's have a look at how it might play out. So first of all, we need to think about what we mean by when we say a change is made to a system that's at equilibrium. By a change, what we mean is any physical or chemical change that results in Q no longer equaling K. So a system that is at equilibrium has Q equal to K. So what's going to happen is we're going to start with Q equaling K. We're going to knock it out of equilibrium. Q will no longer equal K. And then the system will spontaneously move so that Q equals K again. So what we mean by the system spontaneously returning to the equilibrium position is that without us doing anything, the system will adjust the amount of reactants and products so that Q equals K once more. So let's look at this reaction here. We have methane reacting with hydrogen sulfide to give carbon disulfide and hydrogen gas. And we could write QC for this system like thus. We just have our products over our reactants, and everything is raised to the power of the stoichiometric coefficients. When the system is at equilibrium, Q will equal K. Now, if I was to add some methane to this system, that would result in the bottom line here getting bigger, which would mean that Q would get smaller. So initially we're at equilibrium and Q equals K, and then we add methane, which results in my bottom line getting bigger. As a result, Q gets smaller. So after adding the methane, Q is now less than K. So in order to bring the system back into equilibrium, we need to increase the value of Q. So how can we increase the value of Q? How can we make it bigger? Well, we need to increase the amount of products. We need to make the top line of our expression for Q bigger, or we could say also that we can decrease the amount of reactants. So what needs to happen is the whole system needs to move to the right. So we can make Q bigger by making the numerator in Q smaller and making the denominator bigger. So what we really mean is that adding methane is going to make the system move to the right. So the net result of adding methane to this system is that we will form more products, or we would say the equilibrium will move to the right. And that is a general result. Adding reactants always results in the equilibrium moving to the right. Now, an alternative way of making the system move to the right is to remove products. Again, that will result in Q becoming less than K, and in order to restore equilibrium, the system will need to move to the right. So we should be mindful that there are two ways of making the system move to the right. We can either add a reactant or we can remove a product. Now, similarly, if we want the system to move to the left, we can add a product or remove a reactant, and the system will move to offset the change that we are making. So the key point here is whatever change we're making, the system will spontaneously shift in order to offset that change. So if you consider this scenario here, the donkey's legs are off the ground. That's not what we would desire. How do we get the whole thing back into equilibrium with the donkey's legs on the ground? Well, we have two options. We can either remove some weight off the back of the cart, or we could add some weight to the back of the donkey. But either way, making either of those changes would force the donkey to back down onto the ground. Now, changes in pressure can also influence systems that are at or equilibrium systems that contain gaseous components. So, changes in pressure can arise as a result of several things. One of the things that we can do is we can change the amount of one of our gaseous components, and in particular, as amount goes up, pressure goes up, and as amount goes down, pressure goes down. We can also change the volume of our reaction vessel, and as volume goes down, pressure goes up, and vice versa. Or we could add an inert gas to the system, and again, the more gas that we add, the greater the pressure will be. So, adjusting the amount of gaseous component works exactly the same as any other phase. When we increase the concentration of a reactant, the system will move to the right. Similarly, if we decrease the concentration of or the pressure of a product, the system will also move to the right. If we decrease the amount of a gaseous reactant, the system will move to the left to replace it. And similarly, if we increase the pressure of a gaseous product, the system will move to the left to consume that added product. Now, understanding how changing volume affects the system that's at equilibrium, we need to recognize two things: that pressure and volume are inversely related, and pressure and the amount of gas are directly related. So, as I decrease the volume, pressure will go up. As I increase the volume, pressure will go down. And as I increase the amount of gas, pressure will go up. And as I decrease the amount of gas, pressure will go down. So let's look at this system. We have the dimerization of NO2 to form N2O4. So say that the system comes to equilibrium with the pressure of NO2 equaling X and the pressure of N2O4 equaling Y. When we're at equilibrium, Kp is the pressure of our product divided by the pressure of our reactant squared. So this would be Y over X squared. Now, if I half the volume of my container, what happens to the pressure? Well, this is going to get halved. So because they are inversely related, the pressure will get doubled. So that means that the pressure of each of my components is going to get doubled. So if we half the volume, we will double the pressure of each component. So initially we had a pressure of X for the pressure of NO2 and a pressure of Y for N2O4, which meant that Kp was Y on X squared. And now we've halved the volume and thus doubled the pressure, which means that Q for this is now going to be 2Y over 2X squared, which is 2Y on 4X squared, or we can say that that is Y on 2X squared. So what has happened to the value of Q? Well, Q is equal to 1/2 of Kp. That is, Q is less than K. So the result of halving the volume is that Q is now less than K. So how is the system going to respond? Well, what's going to happen is the system is going to shift to the right to make Q equal K once more. So by reducing the container volume by half, we made Q be less than K. So the system will respond by shifting to the right so that Q once more equals K. So that was a very complicated example. But if we simply think about how the number of moles of a gas and its pressure are related, we can understand this system much more quickly. So if we look at this equilibrium here, we have 2 moles of gas forming 1 mole of gas as the reaction progresses. So if I reduce the container volume, the pressure will go up. So the question becomes, how can I make the pressure go down? Well, if I make the system move that way, I consume gas and the pressure will go down. So how I make the pressure go down is by reducing the number of moles of gas, which in this case means shifting to the right-hand side. Okay, so if the system moves to the right, the number of moles of gas will decrease, which will reduce the pressure, and that'll bring the system back into equilibrium. So we don't really need to do any extensive calculations to understand how a gaseous system will respond to changes in volume. We just simply need to take a note of the number of moles of gas on either side of the reaction and see what way the system needs to shift to either increase or decrease the pressure, bringing it back into equilibrium. So let's have a look at this one. It says, how will the following system respond to a reduction in volume? So I'm looking here and I have 3 moles of gas here and I have 5 moles of gas here. So shifting right will make the pressure go up, and shifting left will make the pressure go down. So I'm going to reduce the volume, which will make the pressure go up. So that's the change. And then our question is what is the response? Well, the response is to make the pressure go down. And in order to make the pressure go down, I have to shift to the left. So what will happen is the system will shift to the left. And that's it. So as long as we're cautious and we understand how volume, pressure, and amount of gas are related, we can predict how the system is going to respond to a change in the volume of the container. So a reduction in volume will increase the pressure. The system will spontaneously adjust to decrease the pressure. The equilibrium will move to the left. Let's have a look at this one. So it says, how will the following system respond to an increase in volume? So the change that we're doing is to make the volume go up, which means the pressure will go down. So the response will be to make the pressure go up, which means that the number of moles of gas must increase. So let's have a look at what we've got here. On the left-hand side, we have 9 moles of gas, and on the right, we have 10 moles of gas. So if I want the number of moles of gas to go up, I must shift to the right. So changing the volume, increasing the volume in this case, will make the system shift to the right-hand side. So again, spelling it out, 9 moles of gas on the left, 10 moles of gas on the right. If I move to the left, the pressure will go down. If I move to the right, the pressure will go up. I increased the volume, which decreases the pressure. Therefore, the system will spontaneously adjust to increase the pressure. To do this, the system is going to move to the right-hand side. Now, the final way that we can vary the pressure of our system is by adding an inert gas. Now, it's important to recognize that the reaction quotient for a gaseous system is determined only by the partial pressure of each reactant and product. So, if I add an unreactive gas, while it will increase the total pressure, it won't change any of the numbers that are entered into our expression for Q. As a result, adding an inert gas will not cause the equilibrium position to shift. So adding an inert gas does not cause the equilibrium to shift either to the left or the right. It's going to be a kind of a gotcha question if they ask you about this. Adding an inert gas does not cause the equilibrium to move. The next thing we should consider is how temperature changes change the value of K. For an exothermic process, heat is a product. So if we increase T, then we are increasing the amount of products. And so what that means is that we will see a shift to the left-hand side. Now, vice versa, if we were to cool things down and take the product away, then we would see a shift to the right. For an endothermic process, heat is a reactant. So typically, if we increase the temperature, we will see a shift towards products because we are adding a reactant. And if we decrease the temperature, we're removing a reactant and we would see a shift to the left. Now, temperature changes don't just move the position of the equilibrium, they actually change the value of K. So in addition to saying that we see a shift to the left or a shift to the right, we can say when the system shifts to the left, K gets smaller, and when the system shifts to the right, we can say that K gets bigger. It's important to recognize that if we add a catalyst, we will increase the rate at which equilibrium is obtained. The system will come into equilibrium more quickly. However, catalysts increase the rate of both the forward and the reverse reaction to an equal extent. That's because they lower the activation energy of both the forward and the reverse reaction by the same amount. So, catalysts will decrease the time it takes for a system to get to equilibrium, but they won't affect the position of equilibrium. That is, they won't affect the amount of reactants and products that are present when the system is at equilibrium. So it's worth summarizing. If a system's at equilibrium and we make a change, the system will spontaneously adjust to bring it back into equilibrium. Typical ways that we might knock a system out of equilibrium would be by changing concentration or changing the partial pressure of a reactant. Sometimes we will change the partial pressure of a reactant or a product by changing the volume of the system. When we change the temperature of a system, K will normally change. If we consider heat as either a reactant or a product, we can predict in which direction K will change, whether it will get bigger or smaller. And finally, it's important to realize that catalysts, while they do affect the rate at which equilibrium is obtained, they don't affect the position of equilibrium.